Hello. Now we are going to look at the idea of rate of change when we have curves. So other than straight lines, what does the rate of change look like? Well, we know the rate of change means the slope. For a straight line, the slope is always the same, so the rate of change is always the same. But what defines a curve is that its slope is going to be different at different parts of the curve. If I take my green curve here, the quadratic curve x squared minus 2x plus 2, if I take that green curve here, its slope is different all over the place. It never has the same slope in two places. So its slope is always changing. That's why it's not a straight line. So how could I get an idea of its slope? Well, instead of talking about the slope everywhere, I have to talk about the slope in a particular area because it's changing all the time. So as a first attempt, I could say that I would get an idea of the slope between my 2 points A and B, between x is 2 and x is 3. My 2 points A and B, I could use that. I can see the slope between those 2 points is pretty close to the slope of the green curve. So I could use that as a first attempt at understanding the slope of my curves. So I'd just get my coordinates of A and B, I'd write down my slope formula, and I would just sub into it, and I'd get that the slope between A and B, so the average rate of change between A and B, would be run across by 1 and rise by 3. So run across by 1, rise by 3. So that would be the average rate of change. But what happens if I want to know the slope at a particular point? Say if I wanted to know the slope at A. So not over a particular area, not an average rate of change, but an instantaneous rate of change. The rate of change at a particular point. Well, then I'm going to have to use a tool called a derivative, our dy dx, our slope at a point. So if we want to know the rate of change of our slope at the point A, so at A, we're going to be talking about dy dx, our instantaneous rate of change at x is equal to 2, because the x coordinate of A is 2. So what we're going to do is switch to a graph and have a look at what that looks like. So the screen is about to get a little bit brighter. So what we have here is a graph of the same function that we had before, same green curve, but now we have a tangent to that curve. So we need to know the slope at a singular point. So instead of getting a line that crosses our curve at 2 different points, we set up a tangent line. And a tangent line is only going to touch the curve at 1 point. And if we get the slope of that tangent line, then we effectively get the slope of that curve at that point. So what we can do is move our tangent line around until we get to the coordinate of A. I'll get that there. A was at 2, 2, so that's now the coordinate, that's now the location of A. So my tangent to my curve is sitting at the point A. So what's the slope of that black line? That's going to be the slope of my curve at that point. So the slope of that curve is going to be run across by 1 and rise by 2. This point here is the next time that I nicely cross my grid lines. So I go run across by 1, rise by 2, gets me to my next grid line crossing. Or I could run across by 2 and rise by 4, and I get the same thing for my slope. So I have the slope of the tangent to the curve, or the slope of the curve at that point, is going to be 2. So I can go back to my grid and I can write that in. My slope at A is going to be 1 over 2. So run across by 1, rise by 2. What's the rate of change now if we change to a different position? Because we know on a curve the slope is always changing. So we got the slope of the curve, the green line, at x is 2. But what happens if we move to x being 1? So down at the bottom of our valley here, what would the slope of the curve be at that point? So we can move our tangent line around now, until we get to x is 1. And we can see that we have a horizontal line. So at the bottom of our valley, at the bottom of our curve, at the minimum of our quadratic curve, we get a flat line. We get a horizontal line. And if we go across, if we run across by any amount we like, we never rise by anything. So that means our slope is 0 because our rise is 0. So when we come to the bottom of our curves, of our quadratic curves, we're going to find that the slope is always going to be 0. And this is going to be useful to us in the long run. So for right now, we would just say that slope is going to be 0. dy dx at the bottom of our valley is going to be 0. Now we can't always just draw our graphs in order to figure out what the slope is going to be. So we have an algebraic rule for this, and this rule is in our log tables. So we're going to practice using this rule now. And this is called the power rule. So if we have a y is equal to something involving x, so x to the power of something, then dy dx, the rate of change or the derivative, is going to be multiply by the power. So we multiply by n and then minus 1 from the power. So to do the derivative, we would multiply by the original power and then minus 1 from the original power. And the reason for this comes from combining our slope formula with something called limits, which just mathematically lets our points get closer and closer together. That's where this formula comes from, but for our purposes, it's in our log tables and it gives us our dy dx without us having to draw our graph. So let's use our rule here. So we have y is equal to 3x minus 5. Now this is the equation of a straight line, so I actually already know what the slope is going to be. This is in the form y equals mx plus c. So I know that my slope is just going to be 3. So do I get that for my dy dx when I use my rule? So I'm now going to get dy dx, so I write that down. And my dy dx is my x part here. X by itself would be x to the power of 1. So I'm going to have 3 is outside of what I'm doing. I'm getting the derivative of my x part, my dy dx of this. So I would multiply by the power, so multiply by 1. And then I'd have x to the 1 minus 1. Now the 5, or the minus 5 I should say, just goes to 0. Now we can think about this for a few different reasons. We're kind of looking for the slope, and the slope of a constant is 0. You can also think about a constant as starting out with x to the power of 0. But in general, we simply need to know that the derivative of a constant, when we're getting dy dx, anything that doesn't involve x just goes to 0. So this is just going to end up being 0. Anything that doesn't involve x in it just goes to 0 when we take our derivative. So we're just left with this stuff here, and we can put in a plus 0 if we like. For our minus 5 just goes to 0. Now we have 3 times 1, which is going to be easy enough, but we have x to the 1 minus 1. So what ends up happening there? So we have 3 times 1. Now 1 minus 1 is 0. So we have x to the power of 0. And any number at all to the power of 0 is just 1. So any number at all to the power of 0 will always just be the number 1. And this is another thing we have to get used to saying. So we have 3 times, this is just 1, so it's 1 times 1 is 1. So we just have 3 by 1 is 3. So we get the slope that we were expecting, because we know from our y equals mx plus c that our slope should be 3. So that's our dy dx that we just found. Now what happens if we have our quadratic? This is the quadratic that we had drawn here for our green curve. What happens if we try to use our derivative to get the slope, and then we're going to see what happens when x is 2. This was a straight line, so it didn't have an x in the final answer. This one will, because we know the slope of our curve changes all the time. So dy dx is going to be, we multiply by our power, so multiply by the 2, and then subtract 1 away from the power. And the same thing here. I'm going to open up a bracket. We're going to do the x to the power of 1 here. So we're going to have 1 times x to the power of 1 minus 1. Multiply by the power. Multiply by 1. Subtract 1 away from the power. And then plus 0 for our 2. That constant just goes to 0. So then we end up with 2 times 2 minus 1 is just 1. And then we have minus 2 on, this is going to be x to the power of 0. So 1x to the power of 0. And that just ends up being, this is just 1. So we have 2x minus 2 by 1. So we end up with dy dx is just equal to 2x minus 2. So what happens when we sub in x is 2 into that? So if we sub in x is 2 into that, we want to know what happens when x is 2. We have 2 on minus 2. So we're going to say this is when x is equal to 2. And we get 4 minus 2, which is 2. So we get the same slope out as we did from our visual, from our graph. What happens when we get the derivative of this function here? This is just another example. We have 2 on multiply by the power. Subtract 1 away from the power. 12 on. We have x to the 1 here, so it's going to be 1 times x to the 1 minus 1. And the 18 just goes to 0. And we multiply everything out. Sorry, that is dy dx. My apologies. And then we have 4 on, x to the 1 minus 12 on x to the 0, which is just 1. So we end up with 4x minus 12 by 1. So dy dx is just equal to 4x minus 12. And then we can be asked again a little bit like this. We have our green curve here, and we have find the slope of the tangent to the curve when at x is equal to 1. I've drawn that in here, and I can see that my slope of my red line, which is my tangent at x is equal to 1, is going to run across by 1 and rise by 5. So 1 to 5. So I'm expecting my answer to end up being 5 when I get my slope at x is 1. So we'll work that out now. So we continue with our 3 on, open up a bracket. We have multiply by the power, so multiply by 2, subtract 1 away from the power. And then we have minus 1 on, so we have minus 1 of x. And we have x to the power of 1, so 1 times x to 1 minus 1. And our constant just goes to 0. And we multiply that out, and we get 6x to the 1 minus 1 on 1 to x to the 0, which is 6x minus 1 on 1. So our dy dx is just equal to 6x minus 1. And we want to know what that is when x is 1. So at x is equal to 1. And we have 6 on 1. X is 1 minus 1. So 6 minus 1 is equal to 5. So our slope of our tangent to our curve, our instantaneous rate of change when x is 1, that's the slope of our red tangent line, is 5, or 5 over 1, which is what we found from our diagram. So that's how we can use our derivative rule, our power rule that's in our formula tables, to find the slopes of curves. Even though the slopes are continuously changing, we can use this derivative to find the slope for any value of x. And that is what we need for now.